Let me know when you started. Okay. So, hello everyone. My name is Ajmin, and I am the president of Math Club. And today I'm going to talk about parameterizing number fields using prehomogeneous vector spaces. So, this title brings up four questions. What is a number field? What does it mean to parameterize them? What is a prehomogeneous vector space? And how do prehomogeneous vector spaces parameterize number fields? So, let's answer these questions one by one. So, first of all, what is a number field? The short answer is that a number field is an extension of Q. So an example of this is Q adjoin I, which is a quadratic extension of Q. And what I mean by extension is you take your ground field Q and then you add to it a new element, say I, and I is the root of a polynomial x squared plus 1. So I'm extending Q by adding a new number that's not in Q. And this is a finite extension because it's the root of a polynomial. And another example of a quadratic extension is Q adjoins square root of 2. Here, my polynomial is x squared minus 2, and I'm joining a root of that, which is square root of 2. Square root of 2 is irrational, so it's not in Q. So this is another finite extension of Q. And if I compose both extensions, first I extend by Q and by square root of 2, and then add both of them into my field, then this gets me a new field, which is the composition of the previous two. And so this is also a quadratic extension, but it's not just a no, it's not a quadratic extension. It's also a number field because it's a finite extension of Q, but it's bigger than any quadratic extension. It's bigger than both of these quadratic extensions. It contains them as subfields. And some non-examples are Q adjoins pi, which is not a finite extension of Q because this pi element here is not the root of any polynomial. So it's a transcendental element. So this is really an infinite extension. So if I wanted to put a numbers here denoting the degree of each extension, I would put 2 here because that's quadratic and this is quadratic. That's the root, that's the degree of this polynomial. But here, this would be an infinite extension because pi is not the root of any polynomial. And also R contains Q adjoint pi as a subfield. So this is also not a finite extension. All right, so that's what's a number field. And here are some types of number fields. Q itself is a number field. So Q itself is a finite extension of itself. So it's a trivial number field, but it's also the most what we really want to understand. Okay, so and then quadratic number fields are Q adjoins square root of D. So these are all quadratic number fields. The element square root of D here is the root of a polynomial x squared minus D equals 0. And then cubic number fields are Q adjoin omega, where omega is a root of a cubic polynomial. And a splitting field is Q adjoin, so the notation is Q adjoin F, and by F we mean an irreducible polynomial, and when we write Q adjoin F, we mean to adjoin all of the roots of F. So Q adjoin square root of D is a splitting field, but it is also a splitting field in addition to being a quadratic number field. It's a splitting field of x squared minus D. But a cubic number field need not be a splitting field. For example, Q adjoin cube root of 2 is a cubic number field, but it's not a splitting field of the polynomial x cubed minus 2 because there's another root of this guy, which is omega times square root cube root of 2. So this is not inside of this field, but in order to get a splitting field, we needed to join all of the roots. Okay, so that those are different types of number fields. And what does it mean to parameterize number fields? So the square-free integers D, by square-free, I mean it contains no square factors. These integers D parameterize all of the quadratic number fields. So if I have a square-free integer, meaning it contains no square factors, then Q adjoins square root of D is going to be a quadratic number field. And every quadratic number field is of this form. So I have a parameterization of, I've parameterized all of the quadratic number fields. Again, if it's square-free, then square root of D is irrational. So then it's not in Q, and then this is a new number field. So a question is, can we parameterize all of the cubic number fields, or can we parameterize all of the splitting fields of cubics? And your natural instinct might be just to list all of the cubic polynomials, ax cubed plus bx squared plus cx plus d, and just adjoint roots of these polynomials. But the issue here is that different cubics can produce the same splitting field. For example, if I have x cubed minus 1 and a times x cubed minus 1, both of these polynomials these are different polynomials, but they have the same roots, right? If I multiply by a rational number here, that doesn't change what the roots of this polynomial is. So the same roots means it has the same splitting field. So you can't just list all of the cubics and say that parameterizes the cubic number fields, because I have two different cubics and they have the same splitting field, right? Okay. Another type of issue that comes up is when I do a linear change of variables, right? So I have x cubed minus 1, and this has a root omega. And when I compare it to x cubed x plus 1 cubed minus 1, this has a root omega minus 1, right? So a root of this guy, you have a root of this guy if and only if when you subtract 1, your root of this guy, because I just took x and swapped it with x plus 1. So if your root over here, then just having omega minus 1 gives you a root over here, right? So but the issue is that the fields that you get out of this are the same, right? Omega q adjoint omega is equal to q adjoint omega minus 1. So this is another type of issue that appears when you are looking at these when you just list all of the polynomials, right? These are two distinct polynomials, but they produce the same splitting field. So what's the solution? The solution is to identify them, right? Okay, so and this is where the idea of prehomogeneous vector space comes in. And so this prehomogeneous vector space I'm going to describe is called the cubic case, and it's going to parameterize splitting fields of cubic polynomials. So what you have is a vector space V here. V is sim32. So these are the binary cubic forms. So up here, I was looking at cubic polynomials, but I can just homogenize the polynomials by adding, making all of the terms, by adding a new variable y and then making all of the terms equal to degree 3. So here, this is just a cubic polynomial, but I homogenized it by adding these y and y squared, y cubed things to it. So this is my vector space. It's a 4-dimensional vector space. And I want to identify points in this vector space using a group action. And that would be like saying that this polynomial and this polynomial is the same, and saying that this polynomial and this polynomial is the same. So I'm trying to identify polynomials using the action of a group, and then the orbits of this action are going to parameterize the extensions that we care about. So here, my group is going to be GL2, which is the 2x2 invertible matrices. AD minus BC is not equal to 0, and the coefficients are in Q. And the action is going to be given by a linear substitution of the variables, and you scale by the determinant squared. Okay, so I didn't finish writing this, but there's something called the discriminant polynomial, and it takes a vector, it takes a binary cubic form and tells you if the discriminant is equal to 0, that's only if V has a multiple root. And so we just take the complement of the set in V, and then the orbits of G inside of the complement of the 0 set of the discriminant parameterize the cubic extensions that we care about, the splitting fields of cubic polynomials. So this is an example of a prehomogeneous vector space, and the orbits of this action parameterize the cubic extensions that we care about. Okay, thank you. So that has been 10 minutes. Are there any questions?
Yeah, what is the origin of the term prehomogeneous? Do you know?
Yes, good question. Yes. So when I look at this action, GL2 on a sim 3, 2, as long as my field is algebraically closed, let's consider this group over C and this vector space over C. Then there's okay, so I'm going to use a term Zariski dense orbit. So this is going to be the complement of, so my vector space V, and I take the complement of, okay, let me look at the set of V in sim 3, 2, such that the discriminant of V is not equal to 0. So this is going to be an open set, and it's a dense set inside of V. And the point is that under it, as long as it's algebraically closed, like C, this group action, this open set is going to be an orbit itself. This is an orbit, and so I have a Zariski dense orbit, and so that makes this a prehomogeneous space for this. So in the usual terminology, a group acting on a space, X is called homogeneous if X itself is an orbit, right? So if X itself is a single orbit, then it's a homogeneous space for G. Here, I don't have that this is a single orbit, but I do have a Zariski dense orbit. So the closure of this orbit is the whole space. So it's called prehomogeneous because I don't have a single whole space being an orbit, but I do have the closure of some orbit being the whole space. So that's why it's prehomogeneous.
Thank you so much.
Right. And so I was looking at orbits the over C, but if I look at orbits inside of this dense orbit over Q, so I look at the rational points and then the rational orbits, those parameterize the cubic number fields over Q. So that's pretty cool, I think.
Do you mean that over C there's only one orbit in the
Yes.
quotient?
There's this dense orbit splits into many orbits when you look at the rational orbits.
Finitely many or infinitely?
No, infinite. There are infinitely many. Right. So these orbits, the rational orbits parameterize the cubic extensions, and there are infinitely many cubic extensions of Q. Right, and so the null set of this discriminant polynomial also has distinct orbits. But okay, that's a technicality. Anyway, so that's my talk. Are there any other questions?
Is the picture more or less the same for, for a higher degree?
Oh, good question. This is the picture. Am I sharing my whiteboard, right? Okay. Let me grab a, no, the picture is not the same. I have a picture somewhere, but it's not loading for me right now. So okay, I should have prepared that picture.
It's
but
okay.
For example, yeah, you can parameterize quartic rings. Quartic number rings and quintic number rings. Using different prehomogeneous vector spaces. So I believe for quartic, you have to look at pairs of ternary quadratic forms. And for quintic, you need to look at quadruples of alternating quintic forms. And the group actions are something else. So these are other, this is called the quartic case, this is called the quintic case. And for if you want to parameterize degree 6 number fields, then we don't know how to do that. Okay. All right, I think I'll end here.
Okay, so what are we doing next? Are we doing the DRP people first and then the math club people, or the other way around, or a mixture?
Okay, so I think we should take into account people's availability. So I presented first because I'm not available later on. And also Gabby is not available until later on.
Do you have like a time that Gabby will be coming, or no, not known?
Not known. So that was from the chat. She should be
Okay.
around 9:30, but
I don't know if we'll still be here at 9:30. I don't know if this event will take up that much time. Okay, Fiona has class at 7:50, so you should probably go next.
all right.
Then.
Yes. Yeah, go ahead, Fiona.
Are you okay being recorded, by the way?
Yeah, it says a host to stay. Oh, there we go. Okay.
Now you can.
Okay, can you see my screen?
Yep.
Okay, so my name is Fiona Murphy, and I am presenting on the topic of probability and machine learning. So what is machine learning? Machine learning is the process of identifying patterns in data and utilizing these patterns to predict future data or to perform other kinds of decision-making, such as classifying the data. Briefly, this is done by splitting input data into a training set and validation set, training one's machine learning model using the training set, testing the model with the validation set, and looking to optimize the performance measure, which is oftentimes accuracy. Machine learning has a variety of real-world applications, from handwriting recognition to spam filtering and much more. So what are some typical components of machine learning algorithms? Function approximation is the general idea behind examples of supervised machine learning, where we are attempting to map input data to certain outputs. We do not know the target function, and so we are approximating the function that correlates our inputs and outputs. Function approximation takes the form of optimizing the performance measure, as previously mentioned. However, we're not actually maximizing the performance measure, but rather we are minimizing a loss function, which can be thought of as the error rate between the outputs we expect to get and the output values our model predicts. So this works to indirectly maximize our performance measure. The loss function pictured on the slide here as J theta is computed as an average of the loss per sample batch over the entire training set. The function has parameters of weights and biases, which regulate how much the loss of a certain sample should impact the accuracy of the model. So the primary method by which the minimization of the loss function is carried out is known as gradient descent. Gradient descent looks to achieve a minimum in the function by ascertaining where the gradient is equal to 0 or a critical point, as well as determine the direction in which the function decreases the fastest using directional derivatives. And the loss function is gradually reduced by updating its parameters in small steps that move in the direction of the negative gradient. So a neural network is an example of a machine learning model. Neural networks can be thought of as a composition of many different linear functions with activations, or functions that determine how the weighted sum of the inputs is transformed into an output. These linear functions exist in unique layers, which are then chained together with the inner steps of composition defined as hidden layers, as the intermediary outputs are not revealed. So when looking at a computational graph for a neural network like figure 1 presented here, which is just a simple example, the individual nodes each represent a variable, which can be of types ranging from scalars to tensors and so on. Arrows are drawn from one node X to another node Y to indicate that Y is computed via a function that takes X as a parameter. And beginning with our input data, the data is operated on by a function, creating a hidden layer, which is then operated on by another function, whose output is then passed the next hidden layer. This process is repeated until the final output is reached. So tying back in our previous discussion about maximizing the accuracy of our model through minimization of a loss function, neural networks use an algorithm known as backpropagation in order to obtain the gradients of our network with respect to its parameters, which are what is used to minimize the loss function. Backprop in mathematical terms is the chain rule, and so we begin with an output z and evaluate the gradient of each parent of z. This computation is done by multiplying the current gradient by the Jacobian matrix or partial derivatives of the function that produced the current variable. And this is continued until the input, here its theta, is reached. Once the gradients of the weight parameters are computed, the parameters can then be updated in order to increase accuracy. So convolutional networks are a type of neural network that are particularly beneficial for processing data that has a grid-like property, such as images, which are two-dimensional grids of pixels, essentially. And CNNs employ the operation known as convolution in at least one of their layers. The convolution operation involves multiplying a weighting function against the input data values. This weighting function is known as a kernel, and is typically a multidimensional array of weight parameters, while the output of this function is known as a feature map. It is important to note that the kernel is much smaller than the array of inputs, which is useful for applying the convolution operation over every kernel size section of the input data. And this allows the kernel to find a particular feature anywhere in the data, as it is not restricted to detecting the feature in only a particular location. So what exactly is the motivation behind using convolution in the framework of a neural network? Well, firstly, CNNs incorporate sparse interactions. And so instead of employing a separate parameter for each function or interaction between our input data and output data, which is done in traditional neural networks, the kernel contains a fixed set of parameters which it applies uniformly to the entire set of input values as it traverses the inputs. This significantly reduces the number of interactions amongst the data and thus the computational cost of such a model. Another useful property of CNNs is equivariance, meaning that if the input data changes, the output will change in the same way. So in the context of image processing, this is useful when attempting to detect edges or certain features of an image, which may appear in a similar form throughout the image. Because of parameter sharing, the translation of the location of the feature within the image will not prevent the network from identifying that feature. So classification is a type of machine learning problem where the goal is to classify inputs in specific categories. This brings us back to our discussion on function approximation, where we are attempting to estimate a function using a labeled training set, thereby creating y hat equals f hat x, which takes theta as parameter. With this approximated function, we make predictions about the labels of new input data. Since input data can be ambiguous, usually a label is not solely returned, but rather a probability distribution of possible labels is returned. From here, the map estimate or the label with the highest probability tells us which class our data truly belongs to. In image classification, the input is the image or the grid of pixels. The labels that are returned are numeric codes that denote the object or feature that is being detected within the image. And as previously mentioned, CNNs are best for handling image classification, as the mapping of the high dimensional inputs to bins is made most efficient with the aid of convolution. And so this semester, we have worked on a project that combines many of these concepts together. The goal of our project was to classify handwritten mathematical digits and symbols similar to Detectify. This is an example of an image classification problem. So we used a data set containing roughly 400,000 images of handwritten symbols in 82 different classes, which include math digits, alphabetical letters, Greek symbols, and the like. We created a neural network using Keras and trained a portion of the data set on this model. We were able to return the probability distributions of the labels for each image in the data set, as well as the training accuracy, which is the performance measure that we selected for our model, and the test accuracy of the validation set, which is the dropout from our data set. We also were able to create a demo where we can draw a mathematical symbol from one of the 82 classes that we trained our model on. and then save the symbol to be fed through our model, which then returns a label predicting which class the drawing belongs to. And so looking at the results of our project, we see that our model performs pretty well with a training accuracy of roughly 92.7% and a test accuracy of roughly 92.1%. And this slight decrease in the test accuracy of the model is expected, as we know that the train accuracy reflects how many outputs were correctly labeled, given that the labels were known, while the test accuracy classifies novel inputs with unknown labels. However, accuracy is not a foolproof measure of the performance of a machine learning model. We can look at the relevant example of COVID testing. If we had a model that predicted every person who received a COVID test to be negative for COVID, we may still have a high accuracy, meaning that most of the predictions were correct and that the patients were truly negative for COVID. However, by predicting every patient to be negative, we would necessarily be assigning many false negatives as well. In the context of COVID, a false negative can have severe consequences. And so assigning only negatives would signify a poor model. As such, a high accuracy does not tell the whole story when assessing a model's performance and should be evaluated amongst other metrics. And so here's an example of the classification occurring in the model. So we have two images of hand-drawn lambda symbols. However, we can see that the classifier is imperfect, as the first lambda symbol, numbered 87893, is misclassified as an X with a probability of about 65.5%. Although one could maybe see how the classifier might misread this symbol, as the top image kind of has a similar shape to an X. The second lambda symbol, on the other hand, numbered 87920, is an example of a correctly labeled image, as it is predicted to be a lambda with a probability of 97.3%. And now I will exit my slides and show a quick demonstration with our demo. And so I can draw a symbol or digit from one of the 82 classes that we trained our model on. So I'll do a number 2. And hopefully this works. And we see that it did return 2 with the probability. I can also do, let's do a square root. And we return square root. And let's do one more. I'll do a letter. I'll do the letter F. And it returns an F. So that's the project that we worked on this semester, and that is the end of my presentation. Thank you.
Are there any questions?
I have a question.
Hi.
So this classifier that you showed is a fuzzy classifier, meaning like, or at least in the sense I'm using it, you have a probability of each thing you're trying to classify. You have a probability on each class after observing this data. Now, have you ever like looked at maybe some of the difficult to compare cases? Like you drew a 7 that kind of looks like a 2.
Yeah, so we didn't look at that, but that would be an interesting data point to look at to see maybe what the second highest probable class would be, to see how close our 7 is to 2. So like in the lambda situation that I showed, I didn't look at the entire probability distribution of all the labels. I only looked at the most probable assignment, but it definitely would have been something to improve upon, and it would have been interesting to see how close the lambda was to being assigned as the most probable class.
Could you explain again how the model spits out a probability? So what is I guess I don't understand what the probability is telling us.
Yeah, so essentially you are assigning, you're calculating a probability distribution of the 82 different classes that the image could possibly be assigned to. And so the probability that we get is like the map estimate, which is the most likely label for that image. So that's what the classifier is doing. I don't know if that was a better explanation or not.
Yeah, so does that mean that if you, so I guess maybe this is a stupid question, but if you drew the same symbol in exactly the same way, it doesn't mean, and it tells you that it says F with probability 56%, it doesn't mean that 56% of the time it will tell you that's an F. It just means that it won't, by some percentage, it won't tell you it's a different symbol. Is that right, or am I?
Yeah, so I'm pretty sure that what this probability is telling us is yes. So it's just a confidence measure in the class, like which class our image is going to be assigned to.
Okay, thanks.
How much time does it take to train the neural network?
Oh yeah, so it takes quite a long time. I think it takes maybe 30 minutes, but I know before, like early on, it was taking about an hour. But we split in our project, we split the training portion and the predicting portion so that we only have to train once, and then we can just download our model, and then we don't have to wait 30 minutes every time.
That's not a bad time. It's doable.
Yeah.
What language do you use?
We use Python.
What, I guess TensorFlow?
Yeah, TensorFlow. All right, if there's no more questions, thank you so much.
Thank you. So, all right, does anyone else have a preference about talking next? Because if not, we'll just like kind of go in the order that people replied. Okay, it doesn't look like there are any preferences. So I think the first person who said in the chat that they're doing a presentation is Matthew. So you could present next if you don't mind.
And are you good being recorded?
Sure.
Anybody in the future who's not fine being recorded, just tell us before you go. Thank you.
All right, okay. Oop. Okay. Okay, so you guys can all see it, right? All right,
Yep.
so we're going to be talking about Brouwer's fixed point theorem today. It's one of those super famous theorems in math that you can find a bunch of YouTube videos about, but we're going to talk about this one. So the motivating example behind it is, say you're drinking your cup of coffee in the morning, you know, you have your croissants, you have your coffee, you want to pour some cream in there because your coffee is really hot, and you're stirring your spoon around, and you wonder to yourself, is there going to be any molecule of coffee that's going to stay in the same spot after I'm done with my coffee just swirling around? And the answer is yes, there is. That's not to say that there's no coffee that's going to move. You know, if you put the cream in there, you move your spoon around, you know, you're going to homogenize the mixture, but you can guarantee there's always going to be one fixed point. You know, it can travel around here and then circle back. And that's what Brouwer's fixed point theorem tells us. So this is what we're going to discuss. If you have a map G from a disk to a disk, you're always going to have one fixed point G. This is what a fixed point is. After you apply G, it's just going to be in the same place afterwards. So say you're swirling your coffee around, you know, you have your spoon in here. At the start, your particle is here, and then it moves around in this path here, and then at the end, it's the same as where it was before. And you're guaranteed that by Brouwer's fixed point theorem. So to prove this, we're going to need a few things. We're going to talk a little bit about smooth maps, smooth manifolds with boundary. Not really Sard's theorem, but that'll be in the background. So if you know what Sard's theorem is, you know, if you have a map U where U is an open set in Rm to Rp and C is the set of critical points. The other critical points are just, where the rank is less than P for X that belong to U, then the image of f of C is going to have measure 0. So there's some cool corollaries that come from that and lemmas that you can get from that. They just kind of work in the background. So if you already know what that is, then great, but we're not really going to talk about it. All right, so a smooth map is just a map where all the partial derivatives exist and they're continuous. So the easy examples are x's, or the exponential function. So this is just an example. You have x squared y, 5x plus sine y. This is another smooth map. Not super interesting yet, but talk about I'll come up later. Then we have smooth manifolds. So if you have a subset M, you just call a smooth manifold, you call the subset M a smooth manifold of dimension M if you can take the point here and there's some neighborhood where it's locally similar to the Euclidean space Rm. So for instance, you have this line here. This is just we'll call it the open interval from like 0 to 1. You can take any point in here, and there's a neighborhood where it's locally the same as R1. So you can kind of see this is your neighborhood. You have this diffeomorphism here, and because it's diffeomorphic to R1, it's a smooth manifold of dimension 1. The sphere is a smooth manifold of dimension 2. You can take any point on the sphere and it's going to be locally similar to something in R2. So we have a smooth manifold of dimension 2. So we're going to talk about what that was. Smooth manifolds with boundary. So this is the half space. We define it like this. So if we have just x1, this is just a line going out like this. If you have x1, x2, you have x that varies like this, and then you just have the plane, just the first and second quadrants. You don't have the third and fourth. And then the boundary we define as Rm minus 1 crossed with 0. This is the set of Rm. So a smooth manifold with boundary is just a smooth manifold, but you have a boundary, and then it's diffeomorphic to V intersected with the half space here. So it's always easier when you have an example. You couldn't have, if you had something on the boundary here, it wouldn't be diffeomorphic to a region in Rn, but it is a manifold with boundary because this is diffeomorphic to half space. So if we have the disk D2, we define it like this. This is a smooth manifold with boundary S1. So the boundary is the circle here, which is in like green or orange or something, but you can't really see it. This is not a smooth manifold with boundary because you have corners here. So it's not a smooth manifold. The corners keep it from being a smooth manifold with boundary. Actually, I should mention that if you removed the boundary and you just had a square without the boundary here, then that would be a smooth manifold. And that the boundary is always going to be one dimension less than whatever this would be. So now we're going to talk about the proof of Brouwer's fixed-point theorem. We're going to use these two lemmas. We're not going to prove the actual Brouwer's fixed-point theorem, but you can reduce it to a case of lemma 2. And you can use the Weierstrass approximation theorem, and everything can be, or it can be approximated like the smooth map. You can approximate it with polynomial functions and just reduce it down to lemma 2. So we're just going to prove this one because it's easier. And yeah, so lemma 1 says there's no smooth map f from x to the boundary. It leaves the boundary pointwise fixed. So we're going to use that to prove this by contradiction. So we want to prove that any smooth map G from Dn to Dn has a fixed point. So if you take a look here, excuse me. So if you suppose that G has no fixed point, So then you take an x that belongs to the disk. We're just going to be taking n is equal to 2. And this argument will generalize for higher dimensions, but I'm just going to draw it for n is equal to 2 because it's easier that way. So if you take an x that belongs to D2 and f of x belongs to the boundary, so you can't see f of x here, but it's labeled down here. It's just blocked by the tab thing. And you let g of x, or you let f of x be the point near to x than g of x, then f from the disk to the boundary is a smooth map with f of x equal to x for all x that belong to the boundary. And this contradicts lemma 1 that says that you can't have a smooth map with a fixed point. So this proves lemma 2, and then you can get Brouwer's fixed point theorem from reducing the continuous condition to lemma 2. So let's take a look at some examples of Brouwer's fixed point theorem. If you have a rotation, this is an example, you're going to have a fixed point here. So after you apply the rotation, this is going to be the only point that stays the same. All the other points are going to be rotated 90 degrees. One thing that I thought was confusing when I learned this theorem was, what if I translate this disk here 10 units to the right? So I was thinking, okay, well, we have a disk to a disk, and it's a continuous map. So why is this not a, but obviously none of the points are fixed. So why is this not an example? Or why is this not a contradiction? If you remember back to where we defined what a disk was, where x squared plus y, or x squared 1 plus x squared 2 is equal to 1. If you translate it 10 units to the right, you're not going to have it equal to 1 anymore. So that's why it's not a contradiction. So yeah, that's not going to have any fixed points. So what about some examples of Brouwer's fixed point theorem? So they might not be super applicable to everyday life, but it's always kind of fun to know some of these applications. Say you take like a big jug of water and you just shake it a bunch of times. You're guaranteed by Brouwer's fixed point theorem that you're always going to have one fixed point when you're done shaking, as when you started. Last but not least, if you go on Wikipedia, you can find a bunch of examples, but one that was really interesting and kind of short was, if you have a map of a country, you take that map and you go to the country and you lay it down on the ground, there's always going to be one spot. You're always going to have one fixed point. And that fixed point is going to be where you are on the map when you put it there. That's really interesting. So that's the end of the presentation. Does anybody have any questions? No? Fantastic. Okay.
Okay, if there are no questions, then we'll move on. Does anyone else have a preference of presenting next? If not, then it looks like the next person who said they're presenting in the chat is Song. So you could begin your presentation now.
Okay. Can you guys see this screen?
Yes.
Yep, we can.
All right. Hi, I'm Song Park, and my DRP topic was a voting theory, and I'm going to introduce how to find a good voting system and one of the famous theorem of voting theory, Harris theorem. So we start with the definition of voting system. Voting system is a function that receives a collection of transitive preference order and produces a societal preference order and ties along it. You can think of the preference order as a ranking of candidates. And preference order in a voting system should satisfy transitivity, which if A is preferred over B and B is preferred over C, then A is preferred over C. And you could also include the phi sphere. And in this example, you can see that 5 voters have a preference order of A, B, C. 3 voters have a preference order of B, A, C. And 2 voters have a preference order of C, B, A. And this is an example of plurality, which gives you a resulting order from the number of first place votes. So A is received first place by 5 voters, and B is ranked first by 3 voters, and C is ranked first by 2 voters. So our societal preference order is A, B, C. The purpose of voting theory is to find a good voting system. So there are some conditions which can tell whether a voting system is good or bad. First is anonymous. Voting systems should treat all voters equally, so you get the same result even if you swap any two voters' preference order. So dictatorship doesn't satisfy anonymity. Next, we have neutral. Voting systems should treat all candidates equally in this case. So if you swap two candidates' ranking from every voter's preference order, then the final ranking should be swapped. Last one, we have monotone. If a candidate is moved up in a preference order of one voter, then that candidate cannot get worse ranking in the resulting societal preference order. He gets the equal or higher ranking. So we need to find a voting system that satisfies these 3 criteria. We first start with the voting system with 2 candidates. One of the example is majority rule, which puts the candidate in the first place who is ranked first by more than half of the voters. If no one is ranked first by more than half, all candidates are tied. And we have May's theorem, which is in a 2-candidate election with an odd number of voters, majority rule is the only voting system that is anonymous, neutral, monotone, and avoids the possibility of a tie. So the majority rule is the only voting system that satisfies these 3 conditions in 2-candidate voting system. In order to prove May's theorem, we need to show that if a voting system satisfies 3 major criteria, then it is a quota system. And quota system is a system that puts the candidate in the first place who is ranked first by more than Q voters. However, if Q is too low, then we could have multiple first place winners. And if Q is too high, then we could have no first place winner. So to avoid tie, Q should be exactly half of the number of voters, which is majority. So we can conclude that in 2-candidate voting system, majority rule is the best one. But if we move to the voting system with more than 2 candidates, majority rule is not going to be a good voting system anymore because it opens the possibilities of getting ties if no one gets more than half first place vote, like this example. And the easiest way to solve this problem is by plurality, which gets the resulting order from the number of votes for the first place from highest to lowest. So in this example, 11 voters rank A first, 10 voters rank B first, and 9 voters rank C first. So the resulting preference order is A is preferred over B, is preferred over C. But this also has a problem. You can see that the second and the third column voters place A last, which is more than half of the voters, majority number. So the society chooses the first place winner, who is hated the most by a majority. Because we have this problem, even when the system satisfies 3 major criteria, candidate arrow made 5 conditions, which is stronger than the 3 major criteria in order to find a good voting system. First is universality, which you don't restrict the voters on their voting except for keeping transitivity. Second is monotonicity. Voting system should be monotone. Third is independence of irrelevant alternatives. resulting preference between any pair of candidates is only depends on the individual preferences between the pair of candidates. If you want to find the preference between two candidates, you can exclude all other candidates and look for the preference between the pair. You still get the same resulting preference between the pair, even if you move around other candidates freely. The fourth one is citizen sovereignty. In other words, neutrality. Voting system should not be imposed in any way. Non-imposed means that you have all the possibilities of resulting preference order. The last one is non-dictatorship. Voting system should not have a dictator who can decide the resulting preference by himself. Arrow tried to find a voting system that satisfied this five condition, and he concluded that there is no voting system that satisfies all the conditions. So there is no perfect voting system in Arrow's point of view. We want to prove the Arrow's theorem, but it is easier to prove the strong form of Arrow's theorem, which also implies the original version of Arrow's theorem. The difference between the strong form and the original is that we replace monotonicity and citizen sovereignty to unanimity. And our new condition unanimity is if every voter in the election prefers A over B, A should be ranked higher than B in the resulting societal preference order. We prove this by showing that you can always find a dictator in a voting system that satisfies universality, independence of irrelevant alternatives, and unanimity. First, fix candidate B, and in a specific situation, you can find the voter VB that decides the final ranking of candidate B. Now we can show that VB controls the outcome of any pair of candidates except B in every situation. So VB controls the outcome of B in specific situation and controls the outcome of any pair that does not include B in every situation. We can start this process with another candidate A. Then we can find a voter BA that controls the outcome of any pair of candidates except for A in every situation. Here we have overlapping point where BB controls the outcome of B in a specific situation, and BA controls the outcome of B in general situation. So BB and BA should be the same voter. So that voter covers all the preference order except for the preference between A and B. We can find another voter BC that controls the outcome of A and B. And we know that BC is also the same voter. So we find a dictator that controls the resulting preference order. So we concluded that there is no such a perfect voting system. So what can we do? We can weaken one of the errors conditions to find the voting system that satisfies those conditions. If you weaken the unanimity condition by allowing tie, you can say that plurality is a good voting system. If you remove universality by restricting voters to mark approved or not approved instead of the order, you have the approval voting that gets the resulting order by number of approvals. American Mathematical Society uses this voting system in their election, so we can say this is a reasonable one. By weakening independence of irrelevant alternatives, you have intensity of binary independence. That's all for my presentation. Thank you. If you have any questions, please ask me.
Okay, any questions? Okay, is there, let's see. Is there anyone else from the DRP who hasn't presented yet? Okay, so Moses, then you should go now, and then.
Okay, sounds good. Thank you.
Sorry, just a sec. Alrighty. Hi everyone, my name is Moses and I'm a third year math major here at Stony Brook, and my mentor is Jacob. So our topic is the Borromean rings cannot be constructed with perfect circles. So as you can see on the figure, this is an example of the Borromean rings, and the definitions are two parts. So the first one is the three rings are arranged so that no two of them are linked. So as you can see that if you pick any two circles, they're not linked. Let's say the top two, they're not linked. Basically, the right one is stacked on top of the left one. And that's the same thing with the other two combinations. But basically, no two of them are linked, but somehow three of them are linked. So as you can see on the second part of the definition, the configuration cannot be taken apart without breaking one of the rings. So there's no way that you can take apart the configuration without breaking one of the rings. So I have a visual example for you guys. So as you can see, we can easily do the first part. We can put two rings together. They're not linked, obviously, but in order to put a third ring in the configuration, you have to break it. So as you can see, I had to cut the third ring and tape it. So somehow, like I said before, no two of them are linked, but somehow the three of them are linked and they cannot be taken apart without breaking one of them. So the Borromean rings can easily be built as a geometric object in such a way that two of the rings are perfectly round circles of the same size. Then the third ring is represented by an ellipse. So this is pretty obvious. As you can see, I couldn't really find two perfect circles, but it's obvious that you can construct this figure, the left figure, with two perfect circles. But the third ring cannot be a perfect circle, but so they have to be an ellipse. And the question is, can they be three perfect circles? But we just said that they can't be, so we have to prove it. And the proof strategy we're using today is by Ian Agel. It was from the notes that he never published, but basically the strategy is that if we can prove that any collection of rings built with perfect circles can be taken apart, then the Borromean rings cannot be constructed with perfect circles, since they cannot be taken apart. The theorem we have here is if a link consists of disjoint perfect circles that are pairwise not linked, then the link is trivial. So to put it into simple words, it means that if a pair of disjoint perfect circles are not linked, then the link can be taken apart. And trivial just means it can be taken apart. So there is a difference between the link of two circles and the two linked circles. So the definition of two circles to be linked, as you can see on the figure, these two circles are linked, and they generate planes and disks as well. So these are the two circles, the two disks, the two planes, and there's a line that passes through the two circles with an alternating pattern. So I'm going to explain what the alternating pattern means. So these are the two circles, and the alternating pattern just means that the line that's generated by the two planes that passes through the two circles in an alternating pattern. So it never passes through one circle twice without passing through the other. So let's see here, it passes through the first circle, the second circle, first circle, and then the second circle. And it's never the first situation where it passes the first circle twice and the second circle twice, or the second. It's always the third situation where you pass the first one, the second one, and alternates. So the theorem is that if two circles are not linked, then one of them misses or only touches the disk spanned by the other one, resulting in fewer than 4 points on the line L, or the 4 points do not alternate. And to prove this theorem, we take a configuration of n circles in R3 that are pairwise not linked and erect spherical domes above the disks spanned by the two circles. So this is the spherical dome that we span from the circles. And for any circle C in R3 with the center C and radius R, there's a two-dimensional hemisphere as in R4. So as you can see, this is the formula that this is the function that we generate the hemisphere by. And the R4, it's not really in the fourth dimension, but we have a movie basically saying that we just add the variable of time. So we compare the domes basically at one point of time. So we're not really considering the fourth dimension. So why erecting domes? At any point of time when the two domes intersect, well, they don't necessarily have to be two, but it can be a lot of domes. So anytime when the domes intersect, an alternating pattern is forced to be produced, thus linked circles. And we claim here that if two disjoint circles in R3 are not linked, then their spherical domes do not intersect. So we can say it in a different way to prove it. It's that if the domes intersect, then the disks intersect as well. So if you can visualize here, the circle gets smaller and smaller, and at any given time t, it's just a circle. So while the circle shrinks, the center of the circle at the plane spanned by the circle do not change. So the center stays the same, the C stays the same, and the circles stay disjoint since the domes are disjoined by the plane, and thus they remain pairwise, not linked. So as time goes by, it shrinks, it becomes smaller and smaller, and eventually to a point. And so at some time, the circle is so small that does not intersect anymore, does not intersect any plane, and is spanned by any other one of the circles. And the disk spanned by the little circle does not intersect any of the other circle planes. So thus the movie will end with all circles shrunk so far that they have disjoint spanning disks. The circles are completely separate, and thus the link is trivial. Thus the Borromean rings cannot be constructed with perfect circles. And that is the end of the presentation. So are there any questions?
Yeah, I have a quick question.
Yeah.
This might not be particularly fair because I haven't thought at all about this, but the definition of linking you gave, I guess you need these, of course, it's always going to depend on how they're embedded, but you choose a line, right?
Yeah.
Do you know, is there a definition of linking where you have two circles that are embedded in some space, but you don't have straight lines? Like maybe it's not a Euclidean space?
I have no idea regarding the non-Euclidean geometry, I guess, but the line is not generated by the two circles. The line is generated by the two circles where they span the two planes, and the two planes intersect, and that produces a line that goes through the two circles. But they have to be perfect circles. It doesn't work with ellipses, so they have to be perfect circles in order for there to be a line, and it also satisfies the property of the alternating pattern.
Okay, thanks.
I have a question.
Yeah.
Is the converse true? If a link is made out of if a link has three circles and they're perfect circles, they cannot be the Borromean rings?
If they are perfect circles. Oh, but what we essentially did was just to prove that the Borromean rings cannot be constructed this way. So they can't be perfect circles. Not so. At most, two of them can be perfect circles, but the third one has to be an ellipse or something else. It can't be three perfect circles.
I'm saying, does it go the other way? Like if you have perfect circles, then it cannot.
Right, but if we have perfect circles, it's not a Borromean ring.
Okay. I'm just very curious because I have this ring that was sold to me that was said to have this property.
Wow. Let me see. That's That's very interesting. They
And
might not be perfect circles then, I guess. Because, wow. Okay. Could I see that again, please?
yeah,
Wow. Okay.
so there's
Right.
a practical application of your theorem.
That's really interesting. Okay. Yeah, but there could be a lot of possibilities because let's say if they're not perfect circles or they're not, I don't know. I don't know. But definitely they're not perfect circles. I can say that. But yeah.
What do you mean by perfect circle?
Perfect circle. So the distance between the from the center of the circle to the I mean the distance between, so the radius stays the same. So the distance between the from the between the circle to the center of the circle remains the same in the circle.
Okay.
So basically, just like the usual definition of a circle.
Yeah, just like the and it's two-dimensional.
So you mean to build the Borromean ring in 3 space, you have to either use ellipse or somehow bend one of the circle.
Right. Yeah, it could be that.
So it cannot be so like a rigid material. So it cannot.
Right.
Okay.
Exactly.
Well, can I make a comment on Dylan's question?
Yeah, sure.
So in general, if you have 2 circles in the general 3-dimensional space, not Euclidean space, then you can count the number of linking by put a surface that inside the circle, one of the circle. So in this case, you would put a disk inside the circle. And then you look at the other circle that pierces through this surface, and you count the number of times that it pierces through. That would be defined to be the linking number.
You need quite a lot of technology, though, to prove that an embedded circle bounds a disk, right?
Well, sometimes it doesn't. In the case it bounds, then you can define it.
I see. Okay, thanks.
Sure.
All right, any more questions about this talk? Okay, that sounds like a no. Anyone else from DRP who has not presented yet? Okay, so since it seems like the DRP people are done for now, we'll move on to the Math Club people. So that will be May Rose.
Thank you very much. Give me a second. Shift the desktops around. Turn the laser pointer on. Okay, so this is Math with Words, which is a talk about formal semantics. In addition to being a math major, I am also a linguistics major, and this semester I'm taking formal semantics. And Math with Words is how my professor describes the class when he's joking about the fact that some linguistics majors don't like math. I am not one of them. So we'll begin with the most famous quotation about formal semantics from William von Orman Quine: "Logic chases truth up the tree of grammar." And you could just as easily replace logic with semantics here, and the quote would be just as true. And I hope to explore a little bit of what this means in this presentation. So what is formal semantics? Well, we take a step back and we say that linguistics and linguists know a lot about how sentences are put together from nouns and verbs and such. And that's called the study of syntax, which we could talk about another day, but not today. So the question of semantics is how these structures of sentences lead to the meaning of the sentences. And when we say meaning, what we're going to mean is a description of when the sentence is true. So we're going to use rules to write derivations of the truth of sentences is the main goal. First, we need to do a little bit of nitty-gritties before we can talk about formal semantics in full. We need to talk about object language and meta language. Object language is the language under consideration from which we're going to draw the sentences that we're going to analyze for their meaning. Traditionally, sentences in object language are written in quotation marks or italicized if you have italics on in your keyboard. And for this presentation, the object language will be Japanese because it's advantageous to study a language that's not your own because you have may have preconceived notions from the language that you already speak about the meanings of things. Meta language is the language we're using to study the object language, and it will give us the truth conditions. And the truth conditions are the bit that we're going to say tell us when the sentence is true. Sentences in the meta language are not written in quotation marks, and the meta language in this presentation will be English. I'm sorry to non-native English speakers for this. English is my native language, so this is mostly convenient for me. And I think other English speakers in the audience. Now we're going to talk about T sentences. T sentences are how we're going to describe when sentences are true. So they're going to take the form S is true if and only if P, where S is in the object language and P are the truth conditions in the meta language. And when we collect all of the T sentences of a language together, we call it a T theory. Here's an example. I apologize in advance for my bad Japanese pronunciation. This example comes from my class. Hanako ga hashita is true if and only if Hanako ran. How does formal semantics accomplish this goal of creating the T theory? We begin with a grammar, which is not quite what you might expect from what that word to mean. We add lexical rules, phrasal rules, and substitution rules. This builds our semantic theory. And from a semantic theory, we build T sentences. And from the set of T sentences, we get our T theory. What is grammar? Grammar is not a bunch of statements about whether or not you can end a sentence with a preposition or when to use who and when to use whom. Grammar is a description of the possible structures of sentences. And we define it recursively, which means that we can put structures inside other structures. So these are read as a sentence can consist of Hanako ga hashita. A sentence can consist of Yusuke ga aruita. A sentence can consist of sentence, soshite, sentence. A sentence can consist of sentence, matawa, sentence. We ask, what are these rules that we're talking about? Lexical and phrasal rules. Lexical rules give us the building blocks of the sentences, basically the atoms of sentences. And phrasal rules tell us how to put them together into bigger bits. So for example, we have this lexical rule here, which we'll call L1, which tells us that Hanako ga hashita is true if and only if Hanako ran. The second lexical rule we have here tells us that Yusuke ga aruita is true if and only if Yusuke walked. And for our phrasal rules, we'll have this one, which we'll call P1, which says that sentence, soshite, sentence is true if and only if the first sentence is true and the second sentence is true. And lastly, we have this rule P2, which tells us that sentence, matawa, sentence is true if and only if the first sentence is true or the second sentence is true. And we're going to take this or to be the mathematician's or that can mean that both sentence 1 and sentence 2 are true. What are substitution rules? These are the rules that we take from the study of logic, which allow us to substitute one statement for another when we're deriving the truth conditions. here's an example substitution rule called substitution of equivalence. Our derivations are going to look like a series of lines on the left-hand margin and stuff on those lines to the right. So if we have a line that has some stuff and then a circle, a statement called circle, and then some other stuff, and then we have a line here called beta, where we have triangle if and only if circle, where triangle and circle are statements, then we can write the same statement as we had in alpha, but replace circle with triangle. So we have a line gamma, which has the same stuff as alpha, but with triangle in the place of circle, and we cite it as alpha beta substitution of equivalence. And we're going to derive truth conditions now for this sentence. Hanako ga hashita soshite yusuke ga arita. And we have all these rules that we can use. And from these rules and our knowledge of grammar, the grammar that we have, we're going to derive the truth conditions. So let's derive. We're going to begin by using the rule P1, which is this one, which tells us that a sentence, soshite, another sentence, is true if and only if the first sentence is true and the second sentence is true. We don't know when these are true yet, so we're going to leave them in the object language until we figure that out. Next, we're going to use the rule L1, which is our first lexical rule, to tell us that Hanako ga hashita is true if and only if Hanako ran. This is the verbatim quotation of this rule. Then we're going to use, on our third line, we're going to use L2, copying it again verbatim. Yusuke ga arita is true if and only if Yusuke walked. Now we're going to use substitution of equivalence to begin substituting stuff from these statements into this statement. So here we have what I would call circle. Here's circle if and only if triangle. And here's triangle substituted into the original statement that had circle in it. So this is line alpha, beta, gamma. And we cite this as 1, 2, substitution of equivalence, because we get it from the first line and the second line and substitution of equivalence. Next, we can perform substitution of equivalence one more time with lines 3 and 4. And we get our final T sentence, Hanako ga hashita soshite Yusuke ga arita, is true if and only if Hanako ran and Yusuke walked. And we know that this is a T sentence because we have object language on the left-hand side of if and only if, and meta language on the right-hand side of if and only if, and that completes the derivation. Yay, we did it. We wrote the derivation. How am I doing on time?
You're doing good. We honestly have a lot of extra time, so you could take as long as you want.
Okay, I have one slide left. So maybe there's some people out there in the audience who know that sentences aren't actually analyzed like this. Sentences have much richer structure than this, and so do the elements, their elements. In the study of syntax, which is the study of sentence structure, we learn that sentences are made up of noun phrases and verb phrases, which are phrases that contain nouns like Hanako ga, and verb phrases that contain verbs like hashita, and even more stuff like adjective phrases that contain adjectives and prepositional phrases that contain prepositions. We know that verbs have tense, which we can account for in our truth conditions and T sentences. We know that verbs can have modality, which means that we can write sentences like Hanako would have walked or Hanako must have walked. And nouns can have quantity. So we can say things like every girl walked or no person ran. And these are the challenges that modern semantics faces when it analyzes new structures and more. And that's the current state of the theory. Thank you very much. I'll take any questions now.
So I sort of like a question / observation. You know, based on what you showed us, it really just feels like it's literally just, you know, logic, but with a phrase from a different language. And so
well,
is
that's the math with words part.
Yeah. So, and I guess like the point of this last slide is basically that in reality, it's more complicated than that.
Yeah, basically you have to go down more layers. Like I didn't draw any syntactic trees in this presentation, but often you represent these things with trees. And as you make the structure more of the sentence more complicated, you get more layers on the tree. Things get more recursive in your grammar. And you need more rules to account for that.
Okay.
Can I have?
So is the goal kind of to reduce everything to just like a logical thing that we can follow?
Yes, the goal is to write derivations for all the T sentences.
Okay.
Can I ask a question?
Yes.
Do we have to understand the grammar of the meta language to build a T theory for the object language?
In a way, yes.
But then, I mean, it's kind of like a loop. If we want to understand one language, we must understand some other language first. But suppose I don't know anything about any language, then I would never know anything about any language.
Well, that takes us to the question of how we acquire language. And it's assumed that if you are introduced to a language before the age of 12, you can acquire that language fluently.
Yeah, that's kind of mysterious.
That's not the subject of semantics, but it's a very interesting question.
Okay, thanks.
Sure.
Any other questions? Okay, it appears not. So that means I'm presenting next. Unless anyone else decides that, unless there's anyone else who like hasn't presented yet and wants to go now. Okay, I'm going to just connect my tablet to Zoom so that I can present from here. All right, so sharing my screen. Okay, so my presentation is sort of in the form of this poster because this was also the thing I worked on for my honors thesis, and I had to make a poster that was due last week. So this is where I have stuff written up nicely. Of course, like as I'm presenting, I'll like zoom in and write on here a little bit so that, you know, you're not just staring at this massive wall of text the whole time. All right, so let's get started. So the title of this is Belyi-Extending Maps and the Monodromy group of Dessins and fonts. So of course, I'm going to define for you what those words mean. So first, just kind of the abstract of this all, and I'm just going to maybe get a pen out so I can write if I want. So this is kind of dealing with this group that I'm abbreviating as GalQ. So like for those of you who don't know, this is like well, I'll define it in a minute, but basically we don't know a whole lot about this group. And what do we do when we don't understand a group? Well, we have this group we don't understand. We have it act on some other mathematical objects and see if we can get more information about it. So the objects we're acting on to get this information are Dessins and fonts, which I'll also define in a second. And so we want to see like what properties of the scenes are going to be invariant under this action. So there's some invariants we know already, and we also know that we can construct new invariants using something called Belyi-Extending maps, which again, I'll define that in a minute. And basically, we just want to look for any patterns that come up that could possibly help us understand what's going on. So now for the definitions. So a Dessins font is a connected bicolored graph with cyclic edge orderings at each vertex. So what bicolored means, that just means that we have two colors for the vertices. So the colors that usually are used are black and white, and no edge can have the same color vertex on each end. So like if this is, sorry, if this is an edge of your Dessins, one of the vertices has to be black and the other vertex has to be white, which I know it's blue, but pretend it's black and white. Okay. And the cyclic edge ordering means that we're going to number the vertices, not the vertices, we're going to number the edges of the scene, and sorry, people send me disturbing messages. Not really disturbing. For the people who just messaged me telling me to link my poster, sure, I'll send it after I'm done talking. I cannot do these things at the same time. Okay. So the cyclic edge ordering means that at each vertex, we're going to kind of pick an edge to start at and go around in a circle around the vertex. And we're going to list all of the edges that we come across in as a cycle of a permutation. And so this, well, first I'll show you an example of the scene just so you can get an idea of what I'm talking about. So I actually, when I was doing this project, I purchased a bunch of plastic spheres on Amazon so I could draw Dessins on them. So technically it's not a sphere because it has this little, loopy thing, but we're going to ignore that and pretend it's a sphere. So if you look at my camera, you can kind of see I'm holding this sphere. So this is a Dessin I have drawn on here. So this is kind of like what they sort of look like. And you'll see more examples later on. So ultimately, the cyclic edge ordering winds up being something that we can represent as a pair of permutations. So this will be X gamma, Y gamma. And we call this the permutation representation. So X gamma is going to be, first of all, our Dessin is named gamma. So the subscript is just the name of the Dessin. Whatever we name the Dessin will be the subscript of this permutation representation. So X gamma corresponds to the black vertices, and Y gamma corresponds to the white vertices. So they're basically the permutations that we get by forming these little cycles around each vertex. And then finally, once we have these two permutations, we can generate a group with these permutations, and we're going to call that the monodromy group of the Dessin. Okay. And now, so there isn't a second definition of Dessins as well. So it winds up being equivalent to the first one. So, and what this other definition says is that instead of the cyclic edge ordering, we can require that the graph formed by the Dessin is a subset of some oriented compact topological surface X, such that the complement of G in X is a union of finitely many topological disks. So in case you aren't sure what a surface is, I don't know if all the undergraduates know the definition of a topological surface, but basically it's something like a sphere or a torus or a two-hole torus, stuff like that. Those will be our oriented compact topological surfaces. So the Dessin always going to kind of exist on one of those spaces, or as part of one of those spaces. And the connection between these two definitions is kind of illustrated by like this proposition down here. So the equation is 2 minus 2g equals x plus y minus n plus c, where g is the genus of the surface that the Dessins is on. X is the number of cycles of the permutation x gamma. Y is the number of cycles of the permutation y gamma. And z is the number of cycles of the permutation x gamma y gamma. And then n is the number of edges of the graph of the Dessins. So, right, so that's this equation here, and it's a very interesting equation, and I won't give a proof of it, but basically it follows from what we know about the Euler characteristic of a surface. All right. Next, we want to weigh, since, right, there's like a lot of different ways we could draw Dessins. Like, for example, we could have like, well, okay, maybe, yeah, okay. So maybe I'll give two. No, I don't. Never mind. I don't have like a good drawing of this, but there's a lot of times that you could draw two Dessins on a surface, but they wind up being so similar to each other. Like you could easily, like, I guess, deform one into the other. So we want a way to say that whether or not two Dessins will be considered equivalent. So the definition is that two Dessins are equivalent if there exists an orientation-preserving homeomorphism between the surfaces of the Dessins that induces an isomorphism between the graphs of the Dessins. So basically, we want to preserve like things such as, right, like if we have a homeomorphism from the surface to itself. Oh, sorry. I don't know, I feel like maybe I'm over explaining this and I'm stumbling over my words a bit. So I'll just okay, I'm moving to the next sentence now because I think I feel like I'm just over explaining. So kind of if you're not good at picturing, homeomorphisms and stuff moving around with pictures in your head, we can look at this with just permutations, because it also turns out that the Dessins are also equivalent, like if and only if their permutation representations are conjugate to each other. So that means that if we can find some permutation such that if we conjugate, x gamma 1 and y gamma 1 by sigma, and we wind up with the second representation. So we wind up with x gamma 2, y gamma 2 after we conjugate by sigma. If we get this, that means the Dessins are equivalent. I did not mean to do that. No. Okay. So next we're going to talk about topological surfaces and Riemann surfaces, because this also becomes relevant. So the definition of a topological surface, it has a lot of symbols in it. And so basically the main thing to understand about a topological surface is that basically it's a space that when you zoom in really close, it looks like the complex plane. So the way we represent that is by having these charts on open sets that cover the space. And so basically what these charts do is it takes smaller subsets of our topological space and maps them homeomorphically to the complex plane. And we also want to make sure that, you know, when two of these open sets overlap, we will also want to make sure that their charts, when they're composed in this way, give us a homeomorphism. Right, so now a Riemann surface is just a topological surface, except that these maps here are also holomorphic. So, right. And next we want to map, not only, you know, map a space to the complex plane, but we want to map Riemann surfaces to each other. So if we have a map from a Riemann surface S1 to a Riemann surface S2, we're going to say that that map is meromorphic. If we can take, if for any chart phi1 of S1 and any chart phi2 of S2, that we get that this composition over here is a meromorphic function on the complex plane. All right, an important fact to know about Riemann surfaces is that every compact Riemann surface, we're going to mostly be dealing with compact Riemann surfaces here. Every compact Riemann surface corresponds to some irreducible polynomial f of xy. And we also, an important vocabulary term is that we say that if the coefficients of this polynomial lie in a field K, then our Riemann surface S is said to be defined over K. Okay? And now we're going to look at some very important, like, I guess, type of meromorphic functions on Riemann surfaces. So these are called Belyi maps, and they're very important for the study of Dessins Dessins for reasons you will see at the end of this paragraph. So we're going to take a meromorphic map, F from S to P1. So P1 is just the Riemann sphere, which is literally just a sphere. If you want like a picture of it, it just looks like a sphere. Where again, S is going to be a compact Riemann surface. And we want F to be ramified over at most the points 0, 1, and infinity. So basically, ramified essentially means that it has a different, that when it's ramified over a point, it essentially means that the number of points in the preimage of the ramified points is different from the number of preimage points over the rest of the domain. Okay, so if that sounds a little complicated, just think of it like 0, 1, and infinity are different from all of the other points on the sphere. Which I guess, all right, and also another, if just to be clear, right, the Riemann sphere is also kind of just the complex plane union infinity, right? So that's kind of where we're getting the names of these points from. Right, so if we can find a Belyi function like this, then the pair S comma F is called a Belyi pair. And similarly to Dessins, we want to be able to say when two of these pairs are equivalent. So we say that two Belyi pairs, S1, F1, and S2, F2 are equivalent if there exists a homeomorphism from S1 to S2, such that F1 equals F2 of 5. So, right, it just basically, when we compose F2 with this homeomorphism, we get F1. And furthermore, now we want to talk about kind of one of the main focal points of this project that I worked on is a special type of Belyi maps called Belyi-Extending maps. So these are Belyi maps from P1 to itself that are defined over the rational numbers. And furthermore, when we have a Belyi-Extending map, the image of the set 0, 1, infinity will be contained in 0, 1, infinity. So before, in just a regular Belyi map, we would be allowed to map 0, 1, and infinity to anywhere we want. But for a Belyi-Extending map, 0, 1, and infinity have to be mapped to some other point in the set 0, 1, and infinity. And so now an important theorem about Belyi maps is that if a compact Riemann surface, I want to restate that a little bit. So a compact Riemann surface S is defined over the algebraic closure of Q, which I'll write as, Q bar sometimes. It was hard to format that in PowerPoint, so I just wrote it all out. So the compact Riemann surface is defined over Q bar if and only if S admits a Belyi map. So if a Belyi map exists, if a Belyi map exists, we get this, which is a very, very interesting theorem. And also, just for the sake of information, that Belyi maps also turn out to be defined over Q bar. I'm not going to prove that, but it is, the proof of Belyi's theorem is quite long, actually, and that's, a presentation in itself. It actually took like many weeks in my undergraduate seminar to go over that proof when I was learning it. And the reason we care about Belyi maps for the purposes of this project, the reason why I care about Belyi maps is because of this last sentence here. Equivalence classes of Dessins are in bijective correspondence with equivalence classes of Belyi pairs. So that means if we have a Dessin, we can find exactly one. Well, if we have a class of Dessins, so like up to equivalence, because we only really care about things up to equivalence anyway. So if we have a Dessin, basically we can find a Belyi pair that matches up to that Dessin, and that Belyi pair won't match up to any other Dessin up to equivalence. Okay. Here's a picture I took of that Dessin I showed you earlier. So we have one more paragraph of definitions, and then, well, I guess a couple more paragraphs. But this is kind of the last chunk of definitions. So now we're going to talk about this group Gal Q. So what this is, it's basically the Galra group of Q bar over Q. I wrote it out in more words, but this is essentially what it is. It's automorphisms of the algebraic closure of Q that fix Q. And once again, we don't really understand this group very well. It's kind of mysterious. So we want to learn more about it, and so we're going to have this group act on Dessins d'infants. And the way we do that is, if we have a Dessin, we take the Belyi pair of that Dessin, and then, right, the Belyi pair is going to be a compact Riemann surface and the Belyi function. The compact Riemann surface is, what am I saying? The compact Riemann surface is defined by some polynomial, right? We said that before. And the Belyi map is a meromorphic function. So what we're going to do is we're going to basically take an automorphism from the group Gal Q and have it and apply it to each of the coefficients in both the polynomial that's representing the compact Riemann surface and the coefficients of the Belyi function. So that's how we're going to define this this action. Right, and so we still don't really understand this action too well. Right, that's kind of the question is, right, we given this action, can we find like a complete list of invariants of Dessins? So like what are some things that like if we apply these automorphisms to Dessins, like what are the things that have to stay the same? So right, so we do have a list of some invariants, right? So some things that always have to stay the same when you apply this action to Dessins is we know that the numbers of edges, the number of white vertices, the number of black vertices, and the number of faces will be the same under this action. The degrees of the vertices, so the number of edges around each white vertex is the degree of the white vertex, and the number of edges around each black vertex will also stay the same. The number of edges surrounding each face will also remain the same. The genus of the surface will remain the same, and the monodromy group of the Dessins will remain the same under this action. So these are some invariants that we already know, and there are others. I haven't listed all of them here, but we certainly don't have a complete list of all these invariants. If we did have a complete list, then we would understand this group much better. But we don't have such a list, but we want to try to, maybe work towards finding one. And we can actually construct some new invariants pretty easily by using Belyi-extending maps. So if we take any Dessin D and any Belyi-extending map beta, then any invariant of beta of delta is also an invariant of delta. So that means, right, we obtain a new Dessin by applying the Belyi-extending map to our original Dessin D. So this new Dessin is called beta of D. And right, if we apply this Galois action to beta of D, there are certain things that won't change after we apply it to beta of D. So they're invariants of beta of D. It turns out that if something's an invariant of beta of D, it will also be an invariant of the original Dessin D. So it's kind of interesting. So we can actually get some new information this way. And there do actually exist Dessins that agreed on like a lot of previously known invariants, but were able to be distinguished by using this method with Belyi-extending maps. And one of the easier things to look at regarding this is the monodromy group of the new Dessin. So kind of the monodromy group we get after applying a Belyi-extending map will be an invariant of the original Dessin. So we already knew the monodromy group of D is an invariant of D. But now we also know that the monodromy group of beta of D, which could be different, is also an invariant of D. And so now we just want, kind of what I do in this project is I just kind of look at these monodromy groups and play around with stuff a little bit and see if I can find any patterns. Okay, so what I did was I performed all these computations by writing procedures in Maple. So that's, if you see some ridiculous numbers, that's how I got them. I made the computer do it for me. I did not compute these numbers by hand. So first, I just kind of another sort of definition, but not a very complicated one. It's a little annoying to read, but it's easier to explain in pictures. So I'm going to be talking about these things that I call star Dessins. So what they sort of look like is, these are two examples right here, if you look on my camera. So the one that I have over here, this one is what I would call a black 5-star. I call it black because it has a black vertex at the center, and I call it a 5-star because it has 5 edges, and it kind of looks like a star, so hence the name star Dessins. And then this one over here would be what I call a white 6-star. So I call it white because it has a white vertex at the center, and I call it a 6-star because it has 6 edges. And that's kind of the naming convention I use for the star Dessins in the chart below. So basically, well, all right, first I should point out, I forgot to mention that there are that these down here, these 6 maps that I've listed, these are all Belyi-Extending maps, and you don't really have to memorize the formulas for them. But essentially what you need to know is that what I did in this project is I took these Belyi-Extending maps and I applied, these are the maps that I keep applying to the scenes throughout the rest of this presentation. So if you've seen me referencing beta 1 or gamma, that just means I'm talking about that just means that I applied this map to the scene, and so on. That's what you'll see in this spreadsheet here. So again, like I applied all these maps to the star Dessins, and there came out some interesting patterns actually. So I didn't always calculate exactly the monodromy group of all of these Dessins, but I calculated the size of the monodromy group because it was kind of easier to just get the computer to do that for me. So if you'll notice, the black Dessins and the white Dessins, they always have the same monodromy group, because in both cases, remember the permutation representation I mentioned when I was defining the scenes, right? So that's the pair X gamma, Y gamma. So for black Dessins, this representation, since black Dessins, the black stars just have a black vertex at the center and all the edges are going around the black vertex. So for black Dessins, for the black stars, X gamma is just the cycle made up of just going around all of the edges. So there's 1, 2, 3, and so on up to n, up to the number of edges. And then Y gamma for the black stars will just be the identity permutation, because all of the white vertices don't have only have one edge attached to them, so they don't have any non-trivial cycles. Whereas on the other hand, for the white stars, it'll be the other way around. So for the white stars, X gamma is the trivial permutation, and Y gamma is going to be this cycle. But in both cases, the monodromy group is going to be the same because it's just generated by the same 2 permutations. They're just listed in a different order, right? And the fact that they're listed in a different order means that we have 2 non-equivalent Dessins, but the monodromy groups are the same. So we don't really get, so we don't really get any interesting information here. But if we start applying these Belyi-Extending maps, we notice something different. Now there are a few of the maps don't really tell us anything. So for beta 2, beta 4, and xi, these maps, even after we apply the Belyi-Extending map, the monodromy group of the new Dessins, it still has the same size whether we have applied this map to a black star or a white star. But for example, this map gamma here, we actually get a more interesting pattern. So, right, the black if after applying gamma to the black 2 star, we get a monodromy group of size 48. Whereas applying this map to the white 2 star, we get a monodromy group of size 12. And if for the black 4 star, we get a monodromy group of size 384. And for the white 4 star, we get a monodromy group of size 96. And this same pattern continues. So the monodromy group of gamma applied to a black star is always like exactly 4 times the size of the monodromy group applied to of the Dessins that we get when we apply gamma to a white star. And we also get pattern, like not always the exact same pattern. Beta 5 is a little different. Beta 5 is like, well, we get some different numbers, but beta 3 and beta 5 also have patterns that are kind of like this, where for the even numbered stars, we kind of get this easy looking pattern of the monodromy sizes after we apply the Belyi-Extending map. So this is, I don't really know the implications of this. It just kind of looks cool. Because I guess it does tell us that, right? It does say that, oh, since this number we got for the white 2 star is different from this number we got for the black 2 star, right? Since the monodromy group should be invariant, and we got 2 different numbers for these monodromy groups, that means they're not the same monodromy group, which tells us that the black 2 star and the white 2 star are not in the same Galois orbit under the action that we described earlier. But we already kind of knew that for star Dessins, right? Because one of the easier invariants that we already knew was that, right, the order of each vertex has to be invariant, and right, the black 2 star, the order around the black vertex is 2. Well, the degree of the black vertex is 2, whereas in the white 2 star, the degree of the black vertices is 0. Not 0, 1. So we already knew they were different, but maybe this can still give us some insight into just how these Belyi-Extending maps work, so that maybe eventually we could apply them to more complicated Dessins that we don't already know are in different orbits. So that's kind of what I was going for here when I made these computations. It's just kind of helping us see like what's going on with these maps. And I think it is interesting to see that these patterns kind of emerge sometimes. And next, I also found some other kind of examples like this, where I found these are some examples of Dessins that agree on a lot of the other known invariants, but whose orbits can still be distinguished by the Belyi-Extending map xi. So again, what I did was I didn't apply like the gamma or any of the beta maps to these Dessins. I only applied xi to these. And then what I did was after applying xi, I calculated the size of the new monodromy group. So what wound up happening? Okay, I won't go through every single one of these because I know I've been talking a while. But the one that I want to point out more so than the others, and let me just see if I can find the ones that I made models of. Here they are. Okay, so the most important one of my examples here that I want you to focus on, if you forget about all of the rest of these, is these are the Dessins. I drew them on the poster, but I also drew them on spheres where they rightly belong. This is the Dessins that I labeled G2 on my poster. And this is the one I labeled G4 on my poster. So G2 and G4 are special because if you remember all the invariants I listed when I was defining this action, right? So all this stuff in here. G2 and G4 agree on all of these invariants that I listed at the beginning. So if we were only taking into account these original invariants, we wouldn't be able to tell whether or not G2 and G4 were in the same Galois orbit. Because just because they have the same of these things doesn't necessarily mean they're in the same Galois orbit. However, after we apply xi to G2 and G4, if you'll notice here, the new monodromy group after applying xi to G2, so this is like xi of G2, has a monodromy group with that number. Whereas if we apply xi to G4 and we calculate the monodromy group xi of G4, we get that number. Those are very different numbers. So that means G2 and G4, well, xi of G2 and xi of G4 cannot have the same monodromy group. And since the monodromy group of xi of G2 has an invariant of G2 and xi of G4 is an invariant of G4, that means they don't. That means G2 and G4 don't agree on this new invariant. So that means they're not in the same Galois orbit, which is kind of what we, which is the kind of example of something that we were looking for here. All right, so that's the sentence down here. And kind of one last sort of interesting thing to mention is that I didn't draw pictures on the slides for these, so I'll show you the pictures that I drew on the spheres. So these are two Dessins called, this one is called delta, and this one is called gamma. And so these two Dessins were actually studied in another paper. And these are like, in that paper, these two were actually the prime example of Dessins that agree on other invariants but could be distinguished by the map xi, sort of like G2 and G4. So we already know that these two are in different orbits because their xi invariants disagree. So what I kind of did is I switched the vertices of these two. And what I mean by that is I took all of the black vertices on delta and I replaced them by white vertices and vice versa. So I replaced all the white vertices with black vertices. So it's kind of a similar looking Dessins, but all the vertices are switched up. And I did the same thing for gamma. And I called those new Dessins gamma prime and delta prime. And so what I found is that xi also distinguished delta prime and gamma prime from each other. So we were able to tell that these two were in the same, well, in different orbits. Then we were also able to tell using the same Belyi-Extending map that switching, after we switched the vertices, those two switched up Dessins were also in different orbits from each other. The one catch here is that I could, using that method, the monodromy group of xi of delta was the same as the monodromy group of xi of delta prime. So there wasn't really a way to tell that whether or not those two were in the same orbit. So yeah. That's kind of like, those are kind of the things I thought about as I was doing this. And as I kind of mentioned, like, these are not perfect examples because, again, like, some of the Dessins, we already knew they were in different orbits because of other invariants that I listed before. Though again, I still think it is useful to see when these Belyi-Extending maps distinguish them, just because maybe that'll help us understand the Belyi-Extending maps so that we could know when is good to use Belyi-Extending maps in other contexts. And again, there are some known invariants that I didn't even really take into account at all yet. So there are invariants called the cartographic group in the rational Nielsen class. I don't even really fully understand the rational Nielsen class. So I haven't tested these invariants yet to see if my examples were the same for these two invariants, right? So like I haven't checked every single thing, but I still think some of my examples are pretty cool. And that's essentially what I'm saying here. And right, so there's some further questions that we could pursue based on this, right? We could say like, all right, well, I only calculated the star Dessins for the first 10 numbers for the first 10 number of edges. So like, do these patterns, do those patterns I notice, will that continue forever? And another question might be like, the thing I did where I switched the vertices, does that always happen? Like if the Belyi-Extending map tells us these two Dessins are different orbits, and then we switch the vertices, we switch the colors of the vertices of these Dessins. Does the same Belyi-Extending map also tell us whether those switched up Dessins are going to be in different orbits? And then, of course, we could still just try to find more examples of Dessins that agree on previously known invariants, but that we can distinguish the orbits of using Belyi-Extending maps. So, right, all of these things will kind of help us, again, get an understanding of what these invariants are, and then hopefully, eventually, that'll help us piece together an understanding of the group Gal-Q, which, is a huge open question and not anything that I believe that I ever hope to answer in an undergraduate thesis. But right, those are some things to think about. Right, and so that's about it. So these are just references, and my advisor for this project was Professor Lisa Berger, so thank you to her for helping me out. So yeah, that's essentially what I have to say on this. Any questions?
Yeah, I have a question. So are the orbits of the scenes under the Galois action finite? Right. Are there like finitely many Dessins that are that are equivalent to each other?
Those are two different questions. So Dessins being equivalent to each other is not the same as them being in the same Galois orbit.
Oh, okay.
Yeah, Dessins being equivalent to each other basically just means that we can deform the surface in a way that brings the first Dessin to the second Dessin, right? So it's an orientation preserving homeomorphism that brings Dessin 1 to Dessin 2. Whereas the Galois orbits, this is stuff we obtain by right, applying elements of Gal-Q. One example, maybe I'll draw it, is I forget exactly what it looks like, so I'm getting it out of a book. For example, so these are going to be two Dessins that are not equivalent to each other, but that are in the same orbit. Okay, so yeah, these Dessins are, well, you can tell they're not equivalent because, right, these two are genus 0 Dessins, so they're going to live on a sphere. And no matter how you twist the sphere around with an orientation preserving homeomorphism, there's no way you could bring this Dessin onto that Dessin. Like you just can't make them line up with each other. But they are actually in the same Galois orbit. So Dessins can look quite different from each other and still be in the same orbit.
Okay, my question was, if you look at a specific Galois orbit, are there finitely many non-equivalent Dessins in there?
I do not know the answer to that question. Some orbits, yes, there do exist orbits with finitely many Dessins. I guess an example of that could be, just this is called the trivial Dessin. It lives on a sphere and it's literally just like one black vertex, one white vertex, and one edge, right? That's going to be in its own Galois orbit because yeah, there's no other Dessin that we could find really other than that that's going to be in that orbit. Well, actually, okay. If you're not, I think if you're thinking of equivalence classes of Dessins, if you don't want to think of Dessins of two equivalents, then I guess technically, yes, every orbit will have infinitely many, right? Because, right, the trivial Dessin could be this, or it could be this, or it could be that. Like they could be in different lengths and different positions on the sphere, right? But they're all equivalent to each other. But there are infinitely many of them that are all in that equivalence class, and you can kind of do that for every Dessin. So which is why it's kind of easier to just think of equivalence classes of Dessins instead of thinking of there being so many, infinitely many of these. You can just say they're all the same. So yeah, I guess like technically there would be.
Well, can we go back to the table for a while?
Here?
Yeah, well, I noticed two patterns. So one is that if you have n star, either black or white, then the corresponding monodromy size, with whatever function you're using, is going to be divisible by the number n, where n is the number, this n star. And second, if you look at n star and n times m star, for example, 2 star and 3 and 4 star, or 3 star and 9 star, then the corresponding monodromy size also has the divisibility property, namely the monodromy of 3 star would divide the size of the monodromy of 9 star. And this quotient is a power of 3, which is also kind of interesting. And the quotient of the monodromy size of 4 star divided by the monodromy size of 2 star is also a power of 2. So, well, I don't know. It's kind of, well, I'm just observing these patterns, and I wish, is there any explanation of any of the pattern?
I don't really know an explanation for the patterns.
Well, I guess for the first pattern, I'm guessing, right? Because I don't know this topic at all, but it's really interesting to me. So I'm guessing for the n star, the monodromy size is going to be divisible by n. That is because this star has symmetry, which is it's a cyclic permutation. So that is of order n. So that's probably why the corresponding and invariance associated to that is going to be divisible by n. But I don't see how to explain the second pattern, like the 2 star and 4 star is sort of related, and 3 and 6 and 9 are also sort of related.
Yes, it's definitely interesting. There's definitely, I feel like there's a lot to uncover here, like in these patterns. But I don't really have an explanation for it at the moment. I don't know. There is a way. All right, there is a way to draw a picture of like these new Dessins, and maybe like I might have to look at the pictures. It might take a while to explain. Well, I guess it won't take too long to explain. So I guess like if you want to like make pictures of the new Dessins we get after applying the Belyi-Extending map, what you can do is, right, you can draw the picture of the original Dessin. And then And right, since gamma is also a Bailey, it's a Bailey map. So that means it does correspond to a Dessins in font. So you can draw a Dessins based on this Belyi-Extending map. And then what you basically do is you take the Dessins defined by the Belyi-Extending map, and you kind of like overlay it on top of the original Dessins, like on each. So like that's kind of how you get a picture. It would take maybe a little while for me to draw that. I don't know if I should do that now, just for sake of time, because it's a bit of an explanation in itself.
Are there any other questions? Okay, so thank you, Julian. If there are no more questions, we do have one more speaker. So the speaker will be Gabrielle, and so you can share screen and get started.
Okay, thanks. Yeah, I'm going to share my screen. So. Okay. You guys can see it, right?
Yep.
Okay, cool. All right, well, hi everyone, I'm Gabby. I'm a part of the DRP program. So today I'm going to be talking about a specific knot invariant called tricolorability. And over the semester, my mentor, Tobias Shin, we worked on the book like Knots and Links by Peter Cromwell. So this is just one result that we thought was cool. And I'm just going to go over like a few basic definitions of knot theory, go over like what a knot diagram is, how to color a knot, what tricolorability is, and then why we actually care about it. So first, I'm going to go over what the definition of a knot is. So a knot K in R3 is a subset of points homeomorphic to a circle. So there's just one like basic definition of a knot. And in knot theory, we have a specific way of representing these objects that live in like three-dimensional space. We need to project them onto two-dimensional space, so two-dimensional planes. So we have something called a knot diagram that allows us to do that. And it makes it easier for us to study that and study the knot invariance and everything. So next, I'm going to define what a knot diagram is. So a knot diagram is a generic projection with relative height information at the double points. And a double point in the projection is a crossing in the knot diagram. So let me just write that. Okay, so to just go over that again, a knot diagram is a generic projection of a knot with relative height information at the double points, and a double point in the projection is a crossing in the diagram. So I'm going to show you some examples of diagrams, go over what a double point is, what do I mean by like relative height information and all that. So I pasted three diagrams of a knot, three knot diagrams of the same knot. The first two are kind of more like detailed ways of like describing a knot, but diagram C is the one that you're mostly going to see like in most books, in the book that I used and in a lot of papers. So going to zoom in on that. So I said that a knot diagram is a projection with relative height information at the double points. So we need to know what an arc or strand is. You can call it either one. So a strand is just you start at one undercrossing and then go to the adjacent one. So that's one strand. Here's another one, just so you can get an example. So the double point would be where these two strands would intersect. And at that point, we need to have a way to represent which strand is going under another and which one's going over. So we represent the strand that goes underneath the other one as like a broken line, and then the other one that's going over is just continuous. So that's how we describe the double points and what I mean by like relative height information. And this area right here is considered the crossing, and it's really important to like know a lot about the crossings just because it helps us with different knot invariants, specifically also tricolorability. It's going to help us a lot when we actually have to color the knot. So a little example of that. So also I want to go over what an ambient isotopy is. So an ambient isotopy is two knots are equivalent if there's an ambient isotopy between the two. So that means that there's a continuous deformation between two knots. So in knot theory, we're always trying to figure out if two knot diagrams are equivalent. So we want to figure out if there's an ambient isotopy between the two. And we're going to use knot invariants to figure that out. So let me just define what an ambient isotopy is. Sorry. Okay, so just again, an ambient isotopy, we have two knots, they're ambient isotopic to each other if we can continuously deform one knot to get the other one. So what do I mean with these deformations? There is something called Riedemeister moves. Sorry, the phone going off, but there's something called Riedemeister moves that there's 3 different types, and you can do these Riedemeister moves a finite sequence of times to a knot, and you will get the same knot equivalent to the original one. So I'm going to go over what those 3 moves are, just so you guys can know. So the Riedemeister moves. So there's 3 different types, and they're just called type 1, type 2, and type 3. So the first one is just crossing and then uncrossing. The second one, we have 2 strands and then crossing them. And then the third one, like this, is just moving the middle strand, like basically shifting the middle strand. So, oops, like that. So again, just if you guys can hear me because of the phone, you do as many of these moves to any knot, and it will still be equivalent to the original knot you have. So do like a type 1 move as many times as you want, type 2 moves. That knot that you get after doing those moves will be equivalent to the original one. So those are just 3 moves. And then also I'm just going to define what a knot invariant is, because that's what I'm talking about with tricolorability. Tricolorability is an example of that. And a knot invariant is just a property of a knot that's preserved under ambient isotopy. So knot invariant. Okay, So for example, when I get into tricolorability, say we have one tricolorable knot and we deform it, that knot that you have after doing the deformation will still be tricolorable, and vice versa if it's not tricolorable. So that's what I mean by tricolorability being a knot invariant. So next, I'm going to go into what tricolorability actually is. So it is when you're coloring a knot with 3 different colors, but we have specific conditions that you must follow when we color the knots. So I'll just do it right here. A knot is tricolorable if it's strands, which I went over before, so our first condition, more than one color must be used. Then our second condition is at each crossing, okay, so those are 2 conditions. I'm just going to make this smaller. Okay, so a knot is tricolorable if its strands can be assigned 3 colors such that number 1, more than one color must be used, of course, and at each crossing, we must use either only one color or all different colors. So I'm going to do a few examples with 3 different knots to show you what I mean by at each crossing, you have to color, we have to have a specific amount of colors. So I actually have 3 knots here. So the first knot is just the unknot, that's the trivial knot. You'll notice that there's no crossings there. The second knot is a trefoil knot, and then the third one is the figure 8 knot. You can kind of see why it's called the figure 8 knot. So I'm gonna go over how I'm gonna color these. 2 of these are not gonna be tricolorable, and then 1 of them will be. So first, for the unknot, usually you would start at the at any undercrossing and then go to the next undercrossing. But since we have no crossings here, I'm just going to start anywhere and then keep going. And we never stop. So this is only 1 color. So since we only used 1 color in the unknot, it's not tricolorable because it doesn't satisfy our first condition. So that one is not tricolorable. Next, we have the trefoil knot. So we'll start at 1 undercrossing, go to the adjacent one, and always make sure you don't stop at the overcrossing. You see how there's an overcrossing here? We don't stop there. We have to stop at the undercrossing. Next color, and then here. So we colored all the strands, and now we have to look at each crossing and make sure that we are following the condition. So at our first crossing, we have 3 different colors, so we're good. And then the other 2, we have the same thing. Therefore, the trefoil knot is tricolorable. Next, the figure 8 knot. So I'm going to color that real quick, just using the same process as I used before. And now that we already used 3 colors, we don't want to use a 4th one. So this last strand, I'm going to use a color that we already have and look at the crossings and see what happens. So I'll do green again. If we look at this crossing, it works because we have 3 different colors. But if we look at this one, it does not work because we have 2 of the same color and then 1 different. So therefore, that we just need 1 crossing for it not to work. So this is not tricolorable. I'll just color it a different color so we remember this one's not tricolorable. So those are just how to color knots. It's really easy. And why we care about coloring knots and what does it really tell us. So as I said before, tricolorability is a knot invariant. So it's going to help us distinguish 2 knots from another. So if I know that one knot diagram is tricolorable, I know that it can't be equivalent to any of the not tricolorable knots. So that means we know that it can't be ambient isotopic to the unknot, which is a big question in knot theory, trying to figure out if two knots are different or if they're even like ambient isotopic to the unknot. So it's not a very strong invariant, because if we know that one knot is tricolorable, it doesn't mean that, oh, it's equivalent to all the other tricolorable knots. You're going to have to use other invariants to figure that out, like some of the polynomial invariants, like maybe a linking number invariant, but I won't go over those today. But that's just like a little knot invariant that I thought was cool and helps us kind of distinguish knots. So yeah, that was my project. Does anyone have any questions about tricolorability?
Yeah, so to prove that it is an invariant, you show that, is it right that you show that under the Reidemeister moves, this, if it is tricolorable, then under any Reidemeister move, it's still tricolorable, the new diagram?
Yeah, I can actually show that the 3 moves are tricolorable. I was actually going to include that, but I didn't know how much time I would have. So this one, if we look at that one crossing we have here, you can see that it actually uses the first part of our second condition, that at every crossing, it needs to be all the same color. So this is an example of having all the same color, so it works. And we're assuming that that strand is a part of a knot that has, more than one color. Now for type 2. And then trying to remember. I think that one. Make sure I did that right. Okay, so here we have all the same color, 3 different colors and 3 different colors. So we're good with that. And then just the same thing. So this shows that you can do any of these moves and it will still be tricolorable.
Thank you.
No problem.
Anyone have questions? Okay, doesn't sound like there are any questions. So all right, so just a last minute check. Is there anyone who was supposed to present today who has not done so yet? Okay, that also sounds like a no. So, okay, that is the end of the event then. So thank you to everyone who's talked, everyone who came, everyone who asked questions. Great job, everyone.